Welcome to Data Science 1, Probability, even more on sums of random variables. Okay, things we need to remember. We need to remember what independent identically distributed means, normal random variables, exponential random variables, and properties of expectation. IID means independently identically distributed, which means they all come from the same population and that the distribution that gives is the same. So if it's a Poisson experiment, it's always a Poisson experiment, and the parameterization is the same for IID. We can estimate the parameter. We looked at the expectation before. We could do it with X bar, and we could measure the variability around it. But that's good for the mean. But what if we want to know more about the actual data? And so we might be interested in more than just the mean. So what about the exponential distribution? In the last video, we considered the Bernoulli and Poisson. Well, if we have a exponential distribution here, with parameter beta, where it has the expected value of x is beta for all of them, and the variances of xi is beta squared. What's the distribution here? Well, it turns out that it's a gamma. Okay, and that's kind of to be guessed because I mentioned that before when I was talking about the exponential and gamma distributions. So this shouldn't be too far off. It's how many experiments we are waiting to happen and how long it takes for each one to happen is kind of what they correspond to. Here's what the expected values and variances are, and it's not an approximation. So if you know you have an exponential distribution for your experiment, why are you using the central limit theorem if you don't need to? Because you should really use the distribution that's most appropriate. So here's total time amount it takes for n Bernoulli outcomes to occur. All right, what about the normal distribution? Well, if they all have the same mean and variance, then we're going to let them all come from the mean, the normal distribution, same mean, variance. The sum of them is n mu and n sigma squared. You probably could have guessed that that was going to happen just based off the pattern so far. And again, it's not an approximation. Normal distribution, again, but what if the means are different? Okay, so here we should really take the IID off, and we're just meaning independent. They're all independent of each other, and they all have different means and variances. Well, it turns out that it's normal, and it's the sum of the means, and the variance is the sum of the variances as long as they're independent. Otherwise, you got to count for covariance, and we don't want to do that right now. Okay, squared standard normal distribution. Suppose we have a squared standard normal distribution. Here all the means are 0 and the variances are 1. And we're going to square the standard normal random variable. Well, we want to know what is the y equal to the sum of the square of the standard normals. And you'll see that, well, we remember that 1 standard normal squared gave us a chi-squared 1. So really this is a question, what is the sum of independent chi-squared 1s? And, well, bingo, we end up with that it's a chi-squared with n degrees of freedom. And you could probably guess that that was coming as well because we had mentioned that chi-squared distribution is a flavor of a gamma distribution and exponential is a flavor of a gamma distribution. So this shouldn't be too surprising. But, all right, and again, this is not an approximation like the central limit theorem. Okay, so what did we learn? We know that the sum of IID exponential experiments is gamma. And if they're just independent, you can come up with gamma as well. Normal experiments is normal. Independent normal experiments is normal. The squared standard normal distributions, the sum of those is chi-squared. And there are a lot more of these that you can go look up. I'm just trying to give you the flavor of how these things work. There's lots more that you could look up and work out. But we want to move on to inference, but we need all of these in order to get there. All right, so let's jump into inference, and I'll see you there.